So it's kind of very messy. Now, impact, the impact on detector design. So what do I need to do and know before I design my detector? At least that goes, like, that's why these things take years until they're coming out, and sometimes the problem is that, like, by the time we're about to build it, there is a new technology that came in, so we are working actually of a technology that from 15 years ago, and until everything is built and that, we're putting it and everybody's like, if we had this right now, that would do it so much better. But again, that will take another 10 years to put in. So these things really, it's a lot of people. It's thousands of people, thousands of students that are like the main power of these detectors and accelerator. And so LHC, for example, detector must have fast response. So otherwise, we will be integrating over many bunch crossing. So at least I have to, but already every bunch crossing has 20 interaction, 25 interaction. I don't want more. So I need to be able to separate between bunch crossing. So typical response time that I need is 20 to 50 nanoseconds, because I need separation between the bunch, and during that time I'm able to integrate what happened and stop and go to the next one. So typical response time, I need 20 to 50 nanoseconds, integrate over 1 to 2 bunch crossing. Pile up will mean 25 to 50 minimum bias events. So it's very challenging without electronic that has to deal with this. Now, LHC detector must be also highly granular, because if I have events, because I want to minimize the probability that pile up particles will be in the same detector. I don't want to have, like, if I'm trying to find a Higgs that goes to 2 photons, I want to make sure that these 2 photons didn't enter the same piece of scintillator or piece of cesium iodide or whatever crystal I have. I have to make sure that it's granular enough that each photon enters to a different crystal, so I'm able to separate and reconstruct the P4 of these particles. So I need a large number of electronic channels, and obviously that means high cost. So that's also the other counterbalance to what you ideally want to what you can actually afford. And that's why it's such an international collaboration, because everybody has to pay so much. LHC detector must be radiation resistant. The high flux of particles from the PP collision make the environment very high radiation environment, in the forward calorimeter especially. So you need the resistance to this radiation so it doesn't deteriorate quickly. And the idea is that you want to build a detector that has multiple layers, and every layer will be able to detect different kind of particles. So the innermost layer usually is the one that will be able to detect the charged particles, and what we're trying to do is, usually it's a solid state kind of detectors. They will be here. Then the one that survive and they have enough energy to continue. Basically what I do in detectors is I measure the energy loss. And there's different ways to measure energy loss, either by Compton scattering, Bremsstrahlung, everybody like loses energy. And I kind of collect this energy, and from this energy collection I'm trying to reconstruct the momentum of the particle, the energy and momentum. So if I collect energy, this is for the energy, and if I collect, and if I am able to see the solid state is to actually get the track. So I'm looking at the heat and reconstructing the momentum of the particle. So an electron, for example, will reach here. Pions are coming to here, and will continue. The all charged particles are detected in this. Photon will go through without being detected in the tracking chamber. Then electromagnetic calorimeter, which is based on showering of electron, proton, and photon, will measure these guys, because they will shower inside this electromagnetic calorimeter. Then will come the hadron calorimeter, where hadronic particle like pion and meson and baryons will decay, and they will also shower here, and I will measure these guys. And the last one that survives until the end is the muon. He's very clean, and he goes through the end and I'm able to measure its energy over there and momentum. So you can see all the modern detectors are onion shape. They have this concentric onion layers. Every layer is measuring something else. At the in the middle you have the beam pipe, and then comes the collision, and then they go to different direction, all the mass of particles, and you kind of start constructing your particle identification by first looking at the inner layer that measures the track of the particle by looking at the heats and reconstructing the momentum, then the energy in the electromagnetic calorimeter, energy in the hadronic calorimeter, and then at the end, the muons. So that's kind of a generic way of building a detector today. What are the basic principles? So again, we need a general purpose experiment covering as much as possible of the solid angle. You want to cover as much as possible because everything that you don't measure, you lose. And sometimes you're able to reconstruct the idea of what was it that you lost, and sometimes you can't. So you really want to get as much of the 4 pi as you can. So detector must be able to detect any particle and as many particle signature as possible. The momentum and charge of tracks and secondary vertices are also very important, and that's coming from the central tracker. There are silicon layers in the middle of the detector that are able to measure the heats in the silicon detector, and from the heats I'm able to reconstruct the momentum. The electromagnetic calorimeter is measuring the energy and position of electron and photon, and the energy and position of hadron and jets. Jets are basically pion or baryon that shower in the hadronic calorimeter, so I'm measuring them in the hadronic calorimeter. It's just a different material. Muon are identified and the momentum measured in the external muon spectrometer and the central tracker. And neutrino, which have, let's say, mass 0, are detected and measured through the measurement of what we call missing transverse energy in the calorimeter. So when there is like an energy that is missing, we can do the calculation. What you do is many times is like you come up with an idea of what process you're going to look for. So in this process have a neutrino, you're looking for, you can do the calculation and see what kind of energy spectrum I'm expecting, and then you're looking for it. So that will be the transverse energy in the calorimeter. You can see this is, for example, what is called the CMS detector. And again, we can see the particle as they go through. In CMS, they had a nice idea, and the idea was like, I will put a superconductive solenoid here, so you can see the curvature of the charged particle due to the magnetic field inside the inner layers. So they are curved, and you have to have them curved, otherwise no magnetic field, no curvature, no way to know the momentum. I need the curvature for the momentum. So, and then there's a flux inside here, and that's the return flux. So the return flux goes the other way, so the particle curves the other way. So it curves, for the muon we have curvature inside one way, and then it has to match the curvature on the other side, on the outside layer. And you can see how we actually measure the momentum of charged particles and the resolution of charged particles that are moving in a magnetic field. You can see here, for example, what we're doing is, this is what we call the sagitta. The sagitta is equal r minus r cosine theta divided by 2, which is basically this. This is the sagitta. And for small theta, the approximation is basically r theta squared divided by 8. The momentum of the particle for this kind, and this maybe you should do a small exercise to actually prove this. The momentum is equal to 0.3 b, the magnetic field, times the radius in meters. And this is coming from the force equation, dp to dt. I'm actually doing it, and you can see, you can get that. And I know also that the, how do you call that, L is equal to R theta. I mean this. Forgot the word in English. Sorry?
The arc.
Arc. Yes, arc. Exactly. The arc is equal. It was like meta. R is equal R theta. And if you put them all together, you get that the sagitta is equal to 0.3 b times L squared divided by A times P. So why is that important? First, it connects between some special resolution to momentum that I need, because I need to know how accurately I'm able to measure these things. So the resolution on S determines the resolution on P. So if I want the S to be as small as possible, in order to have a very good resolution on the momentum of my particle. So the N depends on the resolution of the tracking devices, which is the silicon tracker, and we're talking about 10 to 100 micron of the silicon tracker. F is also determined by the state-of-the-art technology, large magnets. So if I want the resolution of my momentum to be very good, that means that I want the magnetic field or the size of my detector to be very big. The bigger it is, I have more points, or I have a bigger magnetic field, I have bigger curvature, I'm able to measure, and if it's bigger magnetic field and bigger curvature, I have a bigger DS, a bigger sagitta, so I'm able to actually measure the resolution of the momentum better. But the problem is that bigger magnetic field is really the state of the art of superconducting magnets, and that's one idea. So one experiment decided, like, we will go and make our magnet as big as possible. So they pushed the envelope, and actually we did a magnet here of 4 Tesla. So that was very big, and it was really a risky experiment. The other collaboration decided we will use the standard superconducting magnet, but we will take a very big magnet, so L will be big. The problem that when L is big, that means it doesn't go, the advantage of using a big L, it goes like L squared, which is good. But larger L, so larger L is better than higher B, but the volume of the detector goes like L cubed. So that means the money as well. So that costs a lot more. So you're like, you win and you lose. So one experiment had a huge detector and the other one had a smaller detector. I find it a cooler detector and a bigger magnet. So I think that was really the right way to go. So the detector challenges of LHC. The LHC are radically different from their predecessor, and they are designed for luminosity of 10 to the 34, energies of 14 TeV, and they need to be fast, radiation hard, and big. Okay, so this is kind of that part of what I want to say about the detector, but now we have the PP collision that are coming and happening at 14 TeV, and what I want to know is what's the luminosity. The luminosity is basically, if I no pen, no thing, okay. So, there's nothing. Okay, so the RDT, anyway, I will try to remember. The RDT is equal to L times sigma, where the RDT is the rate of the interaction per second, and L is the luminosity, and sigma density of the luminosity density, which is the interaction rate per inverse cross-section, time the sigma, which is the cross-section. So, but what is it if we talk about measurable quantities? If I want the luminosity, the interaction rate to be high, obviously what I want is the number of bunches to be very large. I want the number of proton per bunch to be very large. I want the frequency to be very high. So this is all kind of ingredients of what I need in order to make a very high powerful luminosity. And actually, so around the circle of 27 kilometer circumference of LHC, there are 4 detectors, main 4 detectors that were built. 2 are called general purpose 4pi. And why do we have 2? For cross-checking. So you don't want to, one guy say I found the Higgs and the other one I found the graviton, and at the end it's like nobody's checking anybody. So everything that's measured is checked, cross-checked. So that was the main purpose in LHC. So ATLAS and CMS are the competing experiment. Now other groups came, a collaboration, and had their own idea. ALICE is the one that had looking at quark-gluon plasma. They're looking at like it's a heavy ion experiment, and I think they collide lead-lead. And another one is dedicated to detector for studying the B mesons. So there was the one at SLAC at Stanford for many years. This one closed. The one at LHC was like going to the next, so that's called LHCb. Okay, so high interaction rate, we talked about it. We're talking about 10 to the 9 interaction per second. Now the question is, data can only be recorded at about 1,000 hertz, something like that. So 100 out of the 40 million crossing can be recorded, and the rest cannot. So what logic are you using in order to reject the unwanted physics? So here comes the brain of the experiment, and one of the most interesting to me part of the detector is the trigger. There's trigger level 1 trigger and level 2 trigger. Usually some experiments have 3 level triggers, they just divided. The level 1, the main idea is that there are 2 levels of trigger. One will be electronic, that will have to make a decision within 2 to 3 microseconds whether to store the data or to throw it away. So there's a pipeline of data and you have to make a decision. Do I take this physics? I throw it away. So that obviously a computer cannot do yet. So everything here is with electronics, FPGAs and stuff like that. You go, you program them. Today electronic is not like it used to be, like a bunch of things that you solder. Nobody deals with this. Today it's like one U-board tool, like with multiple layers and FPGAs and stuff like that, that you actually write code. You sit in the lab and you write the code for the GPU.